In this video, we're going to be talking about some other characteristics of graphs called critical points. And critical points are any point on your graph where your graph changes its direction or shape. Extrema are points where your graph changes direction. The function has a minimum or maximum value, relative, absolute at these points. So you can see your graph was going up, now it's going down. That's a maximum. Your graph was going down, now it's going up. If it changes its direction, that's called an extrema or an extreme value. A point of inflection is where your graph changes its shape. Now this one sometimes it takes a little bit tougher, it might be a little bit harder to recognize where this is at, but notice your graph coming down through here. It's actually what's called concave up, and then it kind of flips over and it does this thing. So anytime we'll talk about in calculus that it's changing concavity there. So it's coming this way and then it kind of flips over and comes this way. So that's going to be what's called an inflection point. The actual shape of the graph changes there. Okay, relative versus absolute. Let me show you, and it kind of hinted on it up here with relative or absolute maximums or minimums. A relative, it says a point with the greatest value compared to the points around it. That's what's key. Also called a local maximum. It's a relative maximum. I'm just going to put relative max. And what a relative max is, okay, let's look right here at this graph. Here's a relative maximum. Now, is this the highest point on the graph? No. But if you ignore the rest of the graph, pretty much what it means is it's the highest value just right around here. Okay, the same way that the other maximum here, well, this is the highest value right around in here. However, this other maximum, not only is it the highest point just in its area, but it's the highest point on the whole graph as well. So we call that the point with the greatest value over the entire domain, over the whole graph, is called the absolute maximum as well. Not only is it a relative, but it's also an absolute maximum. And the same thing works with minimums. A point with the least value compared to the points around it, just right around it, like this right here. This is the lowest point everywhere around with its neighbors. So that is called a local minimum or a relative minimum. You can relate that to like the relatives in your family, just the ones that are close to you is the minimum amongst them. Now, the point with the least value over the entire domain, over the entire graph, like this one, that's the absolute lowest point on the whole graph. We call that the absolute minimum. Okay, now let's actually find some absolute and relative maximums and minimums, these critical values, and then we'll talk about some inflection points as we go. Give the coordinates and classify the extrema for the graph for each function. Use your graphing calculator to approximate. I've got most of these graphed, but now some of them, like this one, this is a parabola. This is x squared stuff. If you don't remember, the highest or lowest point on a parabola is called the vertex. The way that we find a vertex, this is going back, this is old review. The way we find the vertex on a parabola is by using negative b over 2a. When it's written in the standard form. So we could actually just plug in this b value and this a value and do 16 over 4, so it has an x value of 4. Or we can look at the graph. This relative minimum should occur at 4, and you go down 1, 2, 3, 4, 5. So this 4, negative 5 is not only a relative minimum, but is actually the lowest point on the entire graph. This is an absolute minimum, and it is located at 4, negative 5. And again, just to go ahead and talk about this, that is called the vertex of your parabola. Now the next one's a little bit tougher because we can't hardly tell what these maximums and minimum values are, but we know that we have the absolute highest point on the graph is located right here. Now the lowest point on the graph, do you see that your graph goes down forever? So it does not have an absolute minimum. but it does have a relative minimum. Looking at this small portion of your graph right here, you come down and you hit a low point right here, and then you go back up. And then even though this is not your absolute max, because it was up here, this is the highest point, you do have a relative max here as well, because it changes directions. It comes up and then it goes back down. So you have a maximum here, a minimum here, a maximum here. This is an absolute, this is a relative minimum, and this is a relative maximum. Now let's actually flip over and we'll look at a graphing calculator's rendition of this to find out what the points are. So here I have my function graphed. Again, my absolute maximum, when you're dealing with Desmos, you can simply click on the function and it's going to tell you what that point is. And I'm going to round this thing to the nearest tenth, so about negative 1.5, 2.9. Negative 1.5, comma 2.9 is the location of this absolute maximum. Now let's find this relative minimum right here, which is located here. So that's about 0.3, negative 4.3. 0.3, negative 4.3. That should be a decimal there. And then we have another relative maximum right here, and it is located at 1.3, negative 2.7. 1.3, negative 2.7. So there's all your critical values, or all your maximums and minimums. Now, I call myself when I said critical values because you actually do have one other critical value on this graph. Notice how up here, your graph is kind of concave down, it's cupped down. However, down here, it's cupping up. So you do have, and we'll talk about more of this later, you do have an inflection point somewhere around in here. We can't know exactly where it is without some calculus, but it is going to be somewhere right in here, would be a inflection point as well. Okay, on number 3, you're given this equation, negative x to the third stuff, and I see that I have a change of direction here and a change of direction here. That would be some maximums or minimums. Now, to find out if it's local or if it's relative, ask yourself, is this the highest point on the graph? Is this the lowest point on the graph? And absolutely not. Because look, this graph goes up forever and it goes down forever. So both of these, this maximum and this minimum would both be relative max and mins. So now let's use our Desmos to figure out what the actual points are, because it looks like we can nearly figure out what this is, but the other one does not have an exact lattice point crossing. So here we see the graph, and let's look for our local minimum here first. We have a local minimum. Let me click on my graph at, and that does have an exact crossing, negative 3, negative 5. So let's go back over my relative minimum, and I put these out of order. My minimum is going to be at negative 3, comma negative 5, and you can check that. Left 3, down 5 does look right. Now my relative maximum, again, that's the maximum in this area, so that would be this point right here. Going back to my graph, my relative maximum here would be at negative 0.3, 4.5. So negative 0.3, negative 0.3, 4.5. We also have an inflection point. You can see how this is cupped up. Then all of a sudden here it's cupped down. So it does change directions. Somewhere in the middle here, we would have an inflection point somewhere right in here. Now you might think that it's this dot. It's not necessarily. They're marking this because that's an x-intercept, but your inflection point would be somewhere right around in here. It's where it changes from concave up to down. Okay, number 4, you're going to have some more relative, but you have no absolutes because, again, notice, this graph extends up forever and down forever. So there will be no absolute maximums and no absolute minimums. However, right here, this is the highest point on this hill. Then this would be the lowest point on this hill. Looks like you've got some sort of inflection point right in here to where it changes from up to down. So that kind of bends that around. So we have 2 different extremes here. Let's see if we can figure out what they are. Okay, looking at our Desmos graph, here is the graph of this function. So we have a relative max. Again, this is the highest point in this area at around negative 1.3, 5.9. So let's go back, a max at negative 1.3, comma 5.9. You have a minimum, again, a relative minimum right here, and it is located at 1.3, 0.1. 1.3, 0.1. And again, looks like you actually have some symmetry here that you could actually spin around this inflection point here and you would get the same graph over again. But you do have an inflection point somewhere right in here. It looks to be somewhere around 0.3. But again, we'll talk more about that later on when we hit this value, hit this topic in calculus. Next up, let's talk about increasing and decreasing behavior. Moving from left to right on a graph. A function may increase, decrease, or remain constant on certain intervals. Now, since we are moving from left to right, the biggest thing I need to caution you of is we are looking at x values. So we are telling for which x values is my function increasing, decreasing, or is it constant? For the example on the right, moving from left to right, notice that your graph goes uphill. And you can do it kind of like we did with like you do with piecewise functions. You can divide this into intervals. It's increasing everywhere up to that x value, and then it's constant between those two lines, and then it starts going downhill or it decreases. So reading it from left to right, we're going uphill, we're staying the same, and then we're going downhill. So looking at our x values, let's see, this x value right here is negative 1. This x value here is 1, 2, 3, 4. So to tell where we're increasing, decreasing, and constant, so in interval notation, we're increasing from negative infinity up to negative 1. Now, this is going to be non-inclusive. It's going to be an open interval, meaning that at negative 1, you can't be doing two different things. You can't be increasing and constant because we're actually constant from negative 1 to 4. You see you're staying constant there. So how could you be constant and increasing at negative 1? So that's the reason we don't include it. And then you start going downhill, and you go downhill from 4 forever. Okay, now here's your examples. It says give the intervals on which the each function is increases or decreases. Use your graphing calculator to approximate if necessary. So number 5, I don't think we'll need it. Let me draw my line dividing this graph. It looks like we are decreasing. Let's start over here with decreasing. We decrease from negative infinity up till the line. And again, the line, we use our x values of the line, so we increase everywhere from negative infinity to 4. Then we start going uphill at 4, and we increase from 4 to positive infinity. The second one looks like, okay, we do have an asymptote line here that's going to be a little bit confusing. So let's zoom in and let's take a look at our graph. Let's see, that line's going to be at 1, 2, 3, 4, negative 5. So my graph is going downhill, and it continues going downhill, and that's from negative infinity. That's downhill. So let's try that again. It decreases from negative infinity up to that line at negative 5. Then it jumps from down here to way up here. But here's the thing, it actually starts decreasing again. So the way we're going to write that, it decreases from negative infinity to negative 5, and even though it jumps, it starts decreasing again at negative 5, and it decreases forever. It's slowly tapering off and getting closer and closer to a y value of 1, but it still continued to decrease. So therefore, that had no increasing intervals. Number 7. You can see that reading this thing from left to right, we're going uphill, 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 and we're going uphill forever. Now, where does it start going uphill? This thing does have an asymptote line at right here. So this thing, as you read it from right to left, would go down, 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 getting closer to that asymptote line. But going the other direction, we're increasing forever. So where are we increasing? From negative infinity, actually to positive infinity, because this graph never stops. It continues increasing on and on. So it has nowhere where it's decreasing. Now the next ones, we might have to get some, might have to use our Desmos on these as well to see what these points are. Because again, we need to know our function looks like right here at this minimum value, we're decreasing, and then at this minimum, then we start increasing. And then at this maximum value, it looks like we were increasing, now we start decreasing again. So we need to know this x value, and we need to know what this x value is. So we need to know the x value of this minimum and the x value of this maximum. All right, so let's flip over to Desmos and we see, here's my graph. Let me zoom it different. The x value of this minimum point, and again, we're only concerned with our x values. The x value of this minimum point is located at 0. The x value of this maximum point is at about 2.7. So we can write that on our graph. This is located at 0. This is located at 2.7. So my graph is, first off, it's decreased. When we read it from left to right, we're going downhill for all of these x values, all the way from negative infinity up to my 0, non-inclusive. Then, between those two intervals, from here over to here, we start going uphill. My graph starts going up, and that would be from 0 to 2.7. Then we start going downhill again from 2.7 to positive infinity. So that's your intervals of decreasing and increasing. Number 9, same thing. We need to know what this value is, because at this value, let me draw my lines here. There and then there, it changes direction, and then there it changes directions again. So this thing changes directions 3 times. So my graph over here is going downhill. You notice from left to right, erase that. From left to right, my graph is going down. So we've got to figure out what these 3 intervals are that I've drawn. And here you see a picture of your graph. So let's get, here's our local max minimum, our local max, and our local min. Again, we're only talking about the x values where they're increasing and decreasing. So we have negative 1.8, 0, and 1.1. And there I've labeled them on our graph. So we're going downhill from negative infinity up to that negative 1.8, which is a local minimum. Then you start going uphill, and you go uphill from negative 1.8 to 0. Then you start going downhill again from 0 to 1.1. Then finally you start going uphill again from 1.1 to forever. And then our last one, number 10. Looks like we have a local maximum right there. So you're going uphill until you hit this part. Then you got to be careful. You're actually going downhill and you continue downhill. Even though there's an inflection point in here, you're still going downhill until you hit this point. And at this local minimum, then you start going uphill again. So we've got to figure out what these 2 values are. So let's flip back over to Desmos. And here we see a picture of our Desmos graph. And let me click. There's our local max and min. And notice the similarities there. It's the same numbers, just rotated, which means this graph has a rotational symmetry, meaning that if we spun this thing around, we'd get the exact same thing. So we have a maximum, local maximum at negative 1.1, a local minimum at positive 1.1. So let's go back. So this would be at negative 1.1, and this was at positive 1.1. So my graph in this interval was going uphill, and that would be an increasing from negative infinity until it hits that negative 1.1. Then it starts going downhill, and it decreases from that negative 1.1 up to a positive 1.1. Then it starts going uphill again, and then it increases from 1.1 to a positive infinity.